You probably have heard the rule 1,000 times. Nothing can go faster than light. It's one of those scientific commandments carved into the marble of physics. But here is a twist that makes cosmology feel like a magic trick. Distant galaxies are actually receding from us with a speed faster than light. And yet no law of physics is broken. If you like paradoxes that are secretly simple, stick around. I'll tell you a story. Imagine a giant, invisible grid painted across the universe. And imagine that grid slowly stretching like the rubber sheet of a trampoline being pulled from underneath. The little dots where the grid lines cross. Those are galaxies. They are not zipping through the grid. They're resitting on the grid while the grid grows. This is the simplest picture of the standard cosmological model. Cosmologists call the coordinates that stick to the grid comoving a galaxy that is comoving. Or in other words, a galaxy that sits on the grid keeps the same coordinates, even as the distances between grid points increase. The thing that changes is the scale factor, the number that tells you how big the grid is at any moment. When the scale factor grows, distances between comoving points and between galaxies grow. In the 1920s, Edwin Hubble discovered a simple rule. The farther away a galaxy is, the faster it appears to be moving away from us. For nearby galaxies, there is a linear relationship, recession speed, roughly equals distance times h, where h is the Hubble constant. As you can see, the larger the distance, the faster the galaxy is moving away. There is a special distance where the recession speed equals the speed of light. It is about 14 billion light years. If a galaxy is within that distance, its recession speed is less than the speed of light. But what if a galaxy is further than that distance? This is where the headline friendly paradox comes in. If the distance between us and a galaxy is large enough, meaning larger than about 14 billion light years, then mathematically, the recession speed of the galaxy is larger than the speed of light. Does it mean it is moving faster than light? In one sense, yes. The coordinate recession speed is greater than the speed of light. In another sense, no. No object ever locally outruns light. Inside that galaxy, stars orbit, atoms vibrate, and rockets obey special relativity. Their peculiar velocities, the motions relative to the local grid point, are always less than the speed of light. So we keep two ideas separate. One is the recession velocity, how fast the proper distance between two comoving points, meaning two grid points or two galaxies sitting on the two grid points, changes due to expansion of the grid. This can exceed the speed of light. Second is the peculiar velocity, the local motion of an object relative to its local comoving frame, or local grid point. This obeys special relativity and cannot exceed the speed of light. When people say nothing can go faster than light, they mean nothing can locally outrun light. The expansion of space is not a local motion. It's a global change in geometry. Earlier, we talked about the special distance where the recession speed equals the speed of light. That distance is called the Hubble radius or Hubble sphere. There is a common misunderstanding that the Hubble radius is a hard boundary that light cannot cross. This is not true. Photons emitted by sources outside the Hubble sphere can still reach us, and photons emitted by sources inside can still escape. The Hubble sphere is a snapshot. It tells you the recession speed right now. The expansion rate of the universe changes with time, so the Hubble radius changes too. Let's tell a story about a photon, like a little adventure. Picture a star in the early universe, far beyond the Hubble sphere at the time it emits a photon aimed at us. The photon sets off, but the space between us and the star is stretching very fast. Remember, the star is beyond the Hubble sphere, and hence its receding speed is faster than light, such that the net velocity of the photon, meaning the receding speed minus the speed of light, is positive. This means the photon is flying away from us. It is effectively being carried away by the growing universe, but the expansion rate of the universe changes in many cosmological models The Hubble radius grows with time when the universe is dominated by matter. When the Hubble radius grows large enough, the photon finds itself inside it. In other words, this photon now sits on a grid point where the receding speed is less than the speed of light. Now the net velocity is negative. That means the photon is now flying closer and closer to us, and eventually this photon will reach us. This is not science fiction. It's exactly how we receive light from very distant galaxies. The light we see today may have been emitted when the source was receding faster than light. The photon's path through an expanding universe is a tug of war between the stretching of universe and its constant local speed, meaning between the receding speed of grid points and the constant speed of light. Now let me tell you another story. Imagine the universe as a vast, dark ocean just after the Big Bang, hot, foggy, and glowing. Somewhere out there, 13.8 billion years ago, a tiny ripple of light is born. Let's follow that photon at first. The universe is so dense that the photon cannot get far. It scatters, bounces, ricochets like a pinball in a cosmic arcade. For hundreds of thousands of years, it's trapped in a glowing fog. Then something miraculous happens. The universe cools, the fog clears, and suddenly the photon is free. It shoots right at us. But here, that's the twist. While the photon races at the speed of light, the space it travels through is stretching. Every meter it crosses becomes 2 meters, then 4, then 8. The photon is running on a treadmill that keeps getting longer. Still, it pushes on for billions of years. It weaves through the growing cosmic web, slipping between forming galaxies, dodging clusters, surfing the expanding grid. Finally, after 13.8 billion years of relentless travel, it reaches us, and here is the mind-funny bending part. The place where that photon started is now about 46 billion light-funny years away. That distance, the farthest place from which any photon has ever had time to reach us, is the particle horizon. It's the edge of our cosmic visibility. Not because space ends there, but because light hasn't had enough time to reach us from beyond it. The particle horizon is the farthest messenger we can ever meet today. Now, let's tell the opposite story. The tragic one. Picture a galaxy far beyond the comfortable neighborhood of the Milky Way. It's out near the edge of what we can see, drifting away as the universe expands. Inside that galaxy, a star flares and a photon is born, aimed straight at us. The photon begins its journey with hope. It races forward at light speed, but the space between us is expanding. At first, the photon loses ground. The galaxy is receding faster than the photon can close the gap. But that's okay. Photons have patience, except this time something different is happening. The universe is entering an era dominated by dark energy, a mysterious pressure that accelerates the expansion of space. The stretching of the cosmic grid speeds up. The treadmill beneath the photon runs faster and faster. The photon tries, it runs. It never slows down, but the space between us grows faster than the photon can shrink it. There comes a moment. A heartbreaking moment. When the photon crosses a boundary it can never return from. A point of no return in the expanding universe. That boundary is the cosmic event horizon. Once the photon is beyond it, no matter how long the universe lasts, trillions of years, quadrillions, the photon will never reach us. Not because it's too slow, not because it gives up, but because the universe, as expansion outruns even light, the event horizon is the cosmic never. It marks the region of the universe that will forever remain causally disconnected from us. These two photon stories give us an idea of two horizons. One is the particle horizon, and the other is the cosmic event horizon. These two horizons are different beasts. The particle horizon is about the past. The photon from the past finally reaches us after 13.8 billion years. Even though its starting point is now 46 billion light years away, it is the farthest distance we can see now. The event horizon is about the future. A photon from today will never reach us because the universe, as expansion, outruns it forever. It is what we can never affect or receive. Physics often asks us to separate what we mean by motion. In everyday life, motion is simple, you move through space. In cosmology, motion can mean two things at once: moving through space, and space itself changing. The latter is a geometric phenomenon described by general relativity. When you accept that distinction, the paradox dissolves into a clear picture. The cosmos is a dynamic stage, and sometimes the stage grows faster than the actors can run. That's not a loophole in physics. It's a feature. It's the reason the night sky is a map of history. It's the reason why the most distant light we see was born in the universe that looked very different, and why there are parts of the cosmos that will forever remain strangers to us.